On the other figure we see here is we see a map of Saturn, a top-down view of Saturn's ring plane. In the top left, there are H3 plus intensity variations versus radius. So these come from the observations that I just described in 2011 and 2013. On the upper right, we see essentially the optical depth of Saturn's rings as measured by the Voyager UV instrument, okay? And then on the bottom, we see another sort of measurement of the optical depth or the density of Saturn's rings, and this is just in reflected sunlight. And so what you can see is that some of the structures that we see in H3 plus appear to correlate with some of the structures that you see in the rings themselves. In other words, the rings are somehow interacting with the atmosphere, and that interaction is mediated by Saturn's magnetic field lines, because we can follow the magnetic field line from Saturn's atmosphere, where we see some structures in H3 plus, to where they map to in Saturn's equatorial ring plane, where we see some structures in the rings. Okay? So here's the diagram of Saturn's magnetic field. This does a better job of explaining what I was trying to highlight, which is that Saturn's magnetic field lines essentially come out from the planet and then go through Saturn's ring plane and then go back into the planet. And so, in fact, if you're in one particular portion of Saturn's rings, you can map to a certain latitude in the north, and you're going to map to, along a magnetic field line, to a very similar latitude in the south. I say similar but not exact because Saturn's magnetic dipole is slightly offset from the ring plane. So the equatorial axis of the ring plane and the magnetic equatorial axis are slightly different, okay? But broadly the same. So here's a diagram then of some of the force balance processes that are happening in the rings that might explain why you expect some different regions of the rings to lose mass to the atmosphere and some other regions of the rings to retain the mass in the ring plane itself. Okay? So first we see the main ring system, which is A, B, C, and D. In between A and B is what's called the Cassini division, because there's not a whole lot of mass there. So we've identified then a few of the forces that are acting here. So first is F parallel gravity, meaning this is the force of gravity along the magnetic field line that a charged particle might feel. Okay? Then F parallel mirror and F parallel centrifugal. Okay? So if you're a charged particle and you're stuck to a magnetic field line and it's rotating every 10 hours, that's very rapid rotation, and so you're going to feel a strong outward force called centrifugal force. Okay? That's going to have some component along the magnetic field line. And those are the ones we're interested in. Finally, as let's say you have a force balance between gravity and centrifugal force, and you're at some radius where gravity is slightly winning, then that particle is going to start falling into the planet. If you're within about 1.525 RS, as labeled on this diagram, you can see that F gravity is basically always going to win. Okay? So anything interior of that, if you're a charged particle, you're just going to be sucked into the planet by gravity. Then we see at 1.62 RS, so Saturn radii, charge grains, they start to fall, but they also experience what's called a mirror force. So a magnetic mirror force is when you have converging magnetic field lines. If you're flowing along field lines towards a region where they're converging, you're going to feel a force essentially pushing you opposite of that direction. That's called the mirror force. Okay? So the mirror force helps centrifugal force out in some cases. It balances against gravity. So within about 1.62 RS, gravity is still going to win. However, the mirror force and the centrifugal force are going to start winning over gravity always once you're out in the B ring or say about 1.8 Saturn radii. Okay? Finally, we also label here at 1.95 the Cassini division and 1.83, which is the synchronous orbit. Meaning, if you're a neutral particle in Saturn's rings, the neutral velocity you would be orbiting Saturn at is called the Keplerian velocity. And if you're at 1.83 Saturn radius in the Saturn ring plane, then that neutral Keplerian velocity is identical to what's called the co-rotating velocity, or the velocity of the rotating magnetic field there. Okay? Now, what you can't see in this diagram, but if you go back to a diagram of Saturn's rings versus their density, you can see that a lot of these structures we've identified where forces will balance and where sometimes gravity will win and sometimes it won't, correspond very well with a lot of the density structures you see in Saturn's rings. And so, in fact, we think that Saturn's rings may have been more or less uniformly dense at some point in the past, just after they formed. But then these sort of processes have evolved the rings to the point where they are now. And so this represents a mass loss to the ring system. And in particular, you might see a lot of mass loss in the D ring, in the C ring, and a lot of mass loss in the Cassini division. So here's then a diagram of this ring-ring process altogether, okay? So first, you have Saturn and its ring plane. And in blue, I'm showing essentially where we think Saturn's rings map to Saturn's atmosphere when you follow magnetic field lines, okay? And so these regions are where charged particles from the rings might flow along magnetic field lines into Saturn's atmosphere. I should also mention how you might expect to have charged particles in Saturn's rings. Saturn's rings are predominantly like 99% pure water ice. However, meteorites, micrometeorites, or photons or other energetic particles can impact the rings. And just as they can ionize neutral constituents in Saturn's atmosphere, they can dissociate some of the surface ice at Saturn's rings, and they can create an atmosphere around the rings themselves, and they can also create ionized particles around the rings themselves. And so you may have actual ions, such as water ions, oxygen ions, or you may have denser things such as charged oxygen grains or dust. All of those will feel the forces from Saturn's magnetic field, and therefore they will be subject to the processes that might take them from Saturn's ring plane and its ring atmosphere and link them along magnetic field lines into Saturn's atmosphere. Now, once they get into the atmosphere, they alter the local chemistry. So we'll see how that happens. But what we've seen so far is that H3 plus emissions are either brighter or dimmer based on where you are in latitude in the atmosphere and where those latitudes map to the ring plane, okay? We'll see how H3 plus densities are modified by that chemistry in a bit. The other signatures you see here on the diagram are the bright H3 plus auroral emissions, which are also related to magnetic field phenomenon, but those are at magnetic fields that are very different from the ring magnetic fields that we're describing here, okay? So they're distinct from this phenomenon. So, now the question is, why would you have bright H3 plus emission at some latitudes and then dimmer H3 plus emission at other latitudes? Or in other words, why do you have such variability in H3 plus emission? Because remember I said the ionosphere of the giant planets, and of Saturn in particular, is dominated by solar photon production or energetic particle ionization. And most of that produces H2 plus, which then reacts with H2 to produce H3 plus. And since it's a solar phenomenon, especially at these non-auroral latitudes, that means the source varies smoothly with latitude, the source rate. So to first order, you would then expect to see the H3 plus emissions also be smooth with latitude. So the fact that they're not smooth is some indication that we have additional sources of either ionization or loss. So, in order to investigate how we might have additional sources of loss, we've done a lot of modeling of this process. Here's a figure that shows just an exploration of thousands, hundreds of thousands of different model simulations that explore different influxes of water from Saturn's rings, and also another loss process for H3+, that's related to ionization in the ionosphere. Here I've labeled it as vibrationally excited H2. So all you need to know for our purposes is that it's another way in which the ionosphere might be modified, okay? The chemistry of the ionosphere. So basically, what we've observed is the intensity of H3+ emission. Now the question is that intensity variation due to variations in density of H3+ in the ionosphere, or is it due to temperature variations? Okay, because intensity of this optically thin emission from a gas is a function of the density and temperature of the emitting gas. So, what might happen? As I said earlier, the rings are mostly water, so we might expect that most of the sources that are coming into the rings are also water products. Okay? So let's evaluate what water, H2O, would do if it was introduced into the ionosphere of Saturn. The first thing that it would do is to interact with resident hydrogen ions, so H+, or protons, essentially. And H+ plus H2O gives you a water ion that then recombines with electrons much more rapidly than H+ itself does. So essentially, what that means is if you introduce water or water products into the atmosphere of Saturn, you end up reducing the ionospheric electron density, the ion density and the electron density, okay? If you reduce the electron density, that's a major loss process for H3+. So we can see that reaction here. That's called dissociative recombination. H3+ reacts with electrons to neutralize, essentially. So it removes H3+. This is the dominant loss process for H3+ normally. So if I've introduced water into the ionosphere, that means I've reduced the electron density because I convert a long-lived H+ ion into a short-lived molecular ion, okay? And if I've reduced the electron density, then that means I've reduced the main loss of H3+, or in other words, I've ended up increasing the H3+ density. So if we imagine an influx of water from the ring plane into the atmosphere of Saturn along magnetic field lines, what we would expect to see is a reduction in electron density and an increase in H3+ density. This figure here shows an exploration of the parameter space for how that might happen at Saturn. So this is at one particular latitude, and we've just explored many different variations, possible combinations of water influxes and different loss rates in the ionosphere. And I also highlight the densities that were derived from the observations. Okay, so from the H3+ observations, we can see in the dashed lines the density from the H3+ observations. And then we can compare the model calculations with the observed densities, and we can find families of solutions of combination of different model parameters that would reproduce the observations. Or, in other words, we can figure out what the water flux is from the rings to the atmosphere. So we can use the modeled H3+ density and compare it with the observed H3+ density. And that tells us what the water influx is, or another way to explain it is that tells us what the mass loss is from the rings.